Hi everyone. This lesson is about related rates of change. So the typical scenario for a question like this is we'll have a function y as a function of x, which we've been given here. Now we will typically be told a value for dx dt. So perhaps x is changing with respect to time at a rate of 4 units per second, and we're supposed to find the rate at which y is changing. Now clearly y and x are related, so as x changes, y will also change. And in particular, we want to know the rate at which y is changing when x equals 3. So we've already got dx dt, and we want to find dy dt. So the approach to take is to start with dy dt, that's what we want. Now let's just write this as dy over something, and then something over dt. So the dy and the dt have slid apart. And I'm going to introduce the same thing on the denominator here and the numerator here. Now what would that thing be? Well, dx would be a good choice, because if I put dx in both of these places, then by the chain rule this is true. And I already know that this second part, dx dt, is 4. How could I find dy dx? Well, I could find that by taking a derivative of my original function. So my original function, the derivative would be 12x squared minus 6x, and then multiplied by dx dt. I can substitute 4 for that. So I get 48x squared minus 24x. That's dy dt. Now, we were told to evaluate this when x equaled 3. So, letting x equal 3, we therefore will find dy dt is 48 by 3 squared minus 24 by 3. And when I checked that, that came to the value 360. So that's a very simple introduction to related rates of change. We use the chain rule. Start with the thing that you are looking for, dy dt. Split that into two rates, dy over something and something over dt. Now what do you put there? Well, it depends on what you've got to work with, but typically you'll need to find a derivative of a function, and you'll be given a different rate of change, in this case dx dt. And so that's the chain rule in action, and that's a related rate of change. The rate of change of y with respect to time is related to the rate of change of x by this function over here. Okay, that's a nice short little introduction. Let's do a slightly more interesting example now. So, give ourselves a bit more room. So the next example I want to consider, the first one was just purely algebraic, mathematical. So let's now consider an example where I have a wall, I have the ground, and I have a ladder leaning against the wall. The ladder happens to be 13 meters long. Now, the base of the ladder is sliding away from the wall at the rate of 0.4 meters per second. It happens to be moving at that speed right at the moment when it is 5 meters from the wall. Now this looks like an XY axis. Let's define this distance across the base here from the wall to the bottom of the ladder to be a variable x. Likewise, let's define the distance from the ground to the top of the ladder to be y. That number 0.4 then is the rate at which x is changing. If the base of the ladder moves across the ground, x will get bigger. So this is really dx dt. Now, it's a very good clue that it is a derivative when you look at the unit as meters per second. Meters is a measurement of distance, in this case horizontal distance x, and per second is a unit of time, so divide by dt. It's a very good clue to look at the units to decide what derivative to name this thing. Now our question is to find, obviously as the base of the ladder moves away from the wall, the top of the ladder will slide down the wall, and that's what we have to find. And that would be the rate at which distance y is changing. So that's our unknown, dy dt. And in an example like this, that's probably about all you'd be given. You may not even be told that this is dx dt. You'd simply be told the rate at which the ladder slides away from the wall. Now, we don't seem to have a function this time, but we will use our mathematical sense to form our own function. We would obviously note a right angle triangle here. So Pythagoras would tell us that x squared plus y squared equals 13. Moreover, because we have that x equals 5, we could substitute and solve, and y would be 13. Did I say 13? It should have been 13 squared, Pythagoras. 13 squared, take 5 squared, and we would take the root of that. And because y is obviously above ground, we'll just accept the positive root of this one, not the negative root, and that would come to 12. So we can calculate that. That's easy enough. Now what about our rate of change that we're interested in, dy dt? Let's start by writing what we want to know, dy dt. Now, as we did last time, we'll write this as dy over something else, and then something else over dt. Now, whatever we introduce at both of these gaps will have to be the same. Looking over here, we have dx over dt. It would make sense to put dx here. This way we have a substitution at this point. Now what about dy dx? Well, we can find dy dx from our original function. If we use implicit differentiation, then the derivative of x squared is 2x. The derivative of y squared is dy dx by 2y. And the derivative of a constant is 0. Rearranging this, we will find that dy dx equals negative x over y. The twos will cancel easily enough. And so that's what I'll put over here. Dy dx is negative x over y multiplied by, and we were given that dx dt at this moment is 0.4. Now, using the coordinates, x was 5. We found earlier that y would have been 12, 0.4. And so this will give us the value, when I calculated, negative 0.167 metres per second. Now, let's stop to think, does it make sense that dy dt should be a negative number? Well, yeah, it kind of does, because y, the distance here, will be getting smaller as the top of the ladder slides down the wall. So it is a decreasing value. dx dt is a positive value because x is getting larger as the ladder slides away from the wall. So that all seems to be fitting in nicely. And that's another example of a related rate of change. Remember, always focus on what you have been asked to find. Dy dt was the focus of the question. So I split that derivative into two different rates of change, and then I had to find something in common. Now, why did I choose dx to put into this gap? Because I was given the clue about dx dt. So that gives me the second rate of change as a known value. Then the only other bit, of course, is find dy dx from our function. Now, the thing with these problems is often they won't give you the function. This part here is something that you will have to figure out from the scenario you're working with. And sometimes that can be a bit more challenging than others. But stick with it and you'll get it. Draw diagrams. Diagrams help to prompt your thinking, your mathematical thinking. That's enough for this one. Thanks for watching.